So we've switched gears and we've switched our focus. We're not looking so much about reversibility and about predicting where we are in an equilibrium system. Is it reactant favored or product favored? Anything like that. What we're looking more along the lines of is heat, energy, does a reaction occur? And so as we go through these next three chapters, and we're going to kind of blur through them because by comparison, they're shorter. Those are the things that we're going to have to keep our head on and keep our mind toward. And we will we'll move in that direction and we'll marry the two kind of at the end to talk about where equilibrium fits into this scheme of energy, into this scheme of spontaneity. But that'll be one of the last few things that we talk about somewhere between chapter 12 and chapter 17. So not even this week, sometime next week, we'll get to that. So we're talking about thermochemistry today. And with thermochemistry, this is something that we have some familiarity with. We've talked in thermochemical terms at different points in time in our journey here through this first year of chemistry. But we haven't always done so explicitly. It's just kind of been behind the scenes. We've referenced things. So what we're really looking at is in thermochemistry, we're looking at a subset of a larger branch known as thermodynamics. Thermodynamics is the study of energy and all of the transformations that energy can undertake. It's a very broad physical science topic. Branches out into the world of physics, branches out into the world of engineering, branches out into the world of chemistry. In this first part of this three-part unit that'll make up our third exam, we're going to focus on thermochemistry. Thermochemistry is going to focus on one particular type of energy, heat energy, and looking at the chemical reactions that take place and energy changes that occur as those as those chemical reactions are going on. And so one of the things that we're going to be doing today is we're going to have to set in motion a lot of different terminology and make sure that we are defining our terms clearly and making them distinct from one another. So that's one of the differences that we're going to see between between thermodynamics and equilibrium. There weren't many definitions in equilibrium. There were just different variations on that constant. We're going to see more definitions. We're going to see a little bit more conceptual stuff coming out in this unit. Still going to be tons of math, but there's going to be more other stuff to kind of sink your teeth into and kind of build a knowledge base around, rather than just, oh, here's an equation, put it in there. Here's an equation, put it in there. Here's an equation, put it in there. So let's start with what is energy? By definition, energy is the capacity, that is the ability to do work or to transfer heat. Now, we talked about this concept day one of Chem 105. The idea that work is merely the energy that is required to move an object across some sort of distance. It can be as simple as pushing a chair across the floor. It can be simple as picking up a pencil or throwing an eraser, just not at me. Heat, on the other hand, is the energy that is used or given away to change the temperature of an object, to change the temperature of a substance. When things absorb energy, their temperatures go up. When things release energy, their temperatures go down. And heat is the energy that is being transferred in both of those cases. Now, when it comes to energy, again, this is kind of a basic physical science concept. We all should know the differences between potential energy and kinetic energy. Kinetic energy being the energy of motion. We can calculate the kinetic energy of an object by multiplying its mass times its velocity squared by 1/2. Potential energy we tend to think of as the energy of position or stored energy. Now, there are lots of different types of potential energy. And the type of potential energy we're going to probably focus on the most is the energy that is held inside of chemical bonds. And so that kind of energy that is released when bonds are formed or absorbed to break certain kinds of chemical bonds, we've already talked about in small part when we talked about kinetics. The idea that in order for a chemical reaction to occur, we had to have activation energy. We had to have enough energy present to cause all of the bonds that needed to break so that we could form new ones. But we can summarize all of these different types of energies, the kinetic and the potential, into something called internal energy. Internal energy is going to be the first energy that we're going to assign a letter to. That letter in this case appropriately is E. E for energy. And internal energy for an object or for a chemical system is the sum of all of the kinetic and potential energy stored in that object or series of objects. And we will experience a change in energy being delta E. If you are unfamiliar with delta, that triangle symbol is the uppercase Greek letter delta, and it indicates a change in whatever variable it is attached to. So in this case, it's attached to E. It would indicate a change in the energy of the system. We've seen in other applications delta attached to T, temperature. We've seen in kinetics delta attached to lowercase t in terms of time, or attached to one of these concentration values when we were looking at, kinetics, rates of appearance and disappearance. So that Greek letter delta has been there in places. We just want to make sure we understand that when we see it, that's what it means. And so we will experience these changes in energy when a chemical or physical process occurs and there is a change, a noticeable difference in the energy of the system before the process took place and after the process took place. From a unitary standpoint, the energy unit in question is something called the joule. Now, the joule is a derived unit, it is not a base unit. We can get the joule from the multiplication of kilograms times meters squared divided by seconds squared. For those of you that are physics inclined, if you have taken physics before, you'll notice that this is very, very similar to the unit of the Newton. Newtons, which are a unit of force, are kilograms times meters divided by seconds squared. What's the extra meter for? Well, the application of a force over a distance constitutes energy. So that extra meter is the distance. Now, a joule is actually a relatively small unit of energy. And so for chemical processes, for a lot of different changes, we will often see kilojoules used instead. And the primary reason for that is just instead of expressing a unit of energy in terms of hundreds of thousands or even millions of said units, we can bring it down by a factor of 3. Makes the numbers a little bit more manageable. And as far as significant figures are concerned, makes them a little bit more manageable as well. Now, in terms of energy units, we are actually more familiar with the term calorie. Calories are the customary system unit for energy, customary system being the system that we use here in the United States. By definition, a calorie is the amount of energy it takes to raise the temperature of 1 gram of water by 1 degree Celsius. And so just some conversion kinds of ideas here. 1 calorie is equivalent to 4.184 joules, which again gives you an idea of just how small the joule is, because there are a little bit more than 4 of them in each calorie, which also tells you that the calorie isn't exactly a giant unit of measurement either. And so in a lot of cases, including in nutritional cases, the calories that we associate most commonly with food and beverage items, those aren't actually calories, lowercase c. Those are calories, uppercase c. And the difference in the case is the difference in the magnitude. That uppercase c represents a kilocalorie, 1,000 of those smaller calories. And so that would be the equivalent of a little more than 4,100 joules or 4.184 kilojoules. So again, most of the time, most of our measurements are going to live in this and this area here. Now, that's not to say all of the time. For example, when we do experimental kinds of things, and we'll get to some of those calculations here in a little bit, but when we get to those experimental kinds of things like what we're going to do in lab this morning, The values that we are going to calculate and measure are going to be in joules. And the main reason for that is we are going to be dealing with small amounts of reaction. But if we bring those small amounts up to the molar scale, then they become a lot more problematic. They become a lot bigger. That's where we see kilojoules. That's where we see kilocalories become more useful, is when we're starting to look at things not on the per gram level, but on the per mole level. All right, some more terminology things to kind of uncover. When we are doing thermochemistry and thermodynamic studies, definition of our system and our surroundings become very, very important. And here's what I mean by those two terms. System. The system in question is always going to be whatever portion of the reaction, whatever portion of the universe that we are looking at. I do a chemical reaction. The chemical reaction is the system. Surroundings is exactly what it sounds like. It's everything around the system. So if I do a reaction in solution, the reaction is the system, but the surrounding water of the solution, that's part of the surroundings. Because that water isn't actually participating in the chemical reaction. It's a vessel. Now, if I put the system and the surroundings together, that makes up something called the universe. So in thermodynamic studies, when we say universe, we are not talking about cosmology here. We're not talking about the 8 planets of the solar system and the Milky Way galaxy. We're talking about what is the immediate environment around this reaction system. That environment around the system is the surroundings. If I can put all of that in kind of an encapsulated bubble, that is the universe of this reaction. So we don't need to worry about how the reaction we do inside of our calorimeter is going to affect the air temperature on Neptune, because it's not going to make a difference. So when we say universe, we're not talking astrophysical universe. We're talking about the immediate zone in and around whatever it is that we are studying. When it comes to systems, there are 3 primary types of systems. Which system is present largely depends upon what is able to pass through the system and the surroundings. So we can start with something called an isolated system. An isolated system is so called because we have basically encapsulated the system in such a way that no matter can get into the system from the outside, and no heat can transfer in or out of the system. Good example of that would be, let's say that you have a thermos, sealed off thermos, one of the good ones, not one of, those ones that, loses their temperature after an hour. If the lid is shut and everything is tight, you have as close to an isolated system as you can get commercially. Now, there are better systems out there in environmental settings, in laboratory settings. But in that system, you put your coffee into that thermos, and so long as it stays shut, the heat of the coffee can't get out of the thermos, and nothing else can get into the thermos. That's isolated. A closed system would be like this water bottle. Right now, with the lid shut, no water can get out of this bottle. I can't put anything into the bottle either. But as far as energy is concerned, energy can travel freely through the bottle. I leave it out in the sun, the water gets hot. I put it in the freezer, the water gets cold. That's a closed system. Similar to the isolated system, but without the energy transfer coverage. An open system is exactly what it sounds like. It's completely open. Anything and everything can be transferred in and out of that system. Now, the book gives you an example of a bowl of soup. You can think of other examples as well. But let's say that we do have a bowl of soup. Well, I can eat the soup, which would remove matter out of the bowl. I can add crackers and cheese and all sorts of stuff to the soup, so matter can go in. And if I leave that hot bowl of soup, which is open, eventually it's going to become the same temperature as room temperature. It's going to get cold. So heat transfers in and out freely. Put it back into the microwave, heats up again. Energy transfers can go in, energy transfers can go out. I can eat the soup, I can add stuff to it. Matter can go in and out freely as well. So with that in mind, let's take our first kind of just not like academic break, but let's just see if we got that last point. Here's a question for you. What kind of system would you say is represented by this picture? Multiple choice, should be able to get it in nice and quick. Yeah. 7 said isolated, or excuse me, 7 said open, and that's exactly right. It's open. You've got very clearly here heat being transferred into the water from the burner. And it's open. You can see steam is coming out of it. So we know that it's able to transfer freely that way. All right, let's take a look at another. What type of system is represented here? You don't need to answer again. That's what I was looking for. Okay, this one usually brings about a little bit more debate. And it's usually, I'm glad no one said isolated. A paper coffee cup would not begin to qualify as an isolated system. You can clearly, you hold that cup in your hand and it's going to feel warm. And if it feels warm, that means that the heat's coming out and you're accessing it. So those of you that said closed likely just ignored the top of that coffee cup. With that opening where you can drink out of it, it is technically an open system. Now, it is as closed as an open system can get, but it is still technically an open system. If I wanted to, I'd have to use a straw, but if I wanted to, I could add creamer or sugar to the coffee, and I can certainly drink out of it, which means that matter can go in and out as well. And the same would be true for pretty much any of your, similar kinds of vessels. Slide it open, it's an open system. Keep it shut, it's a closed system. So we've got the idea of those different types of systems. Let's start to kind of put some of these concepts together, and then we'll take our first academic break, and you can get around, up and move and that kind of thing. First law of thermodynamics. This is a concept that we're already familiar with. We already knew from Chem 105, from other classes, the law of conservation of energy. It says that in any process, energy cannot be created or destroyed. It can only be transformed from one form to another. We knew that already. That's nothing new. But it does have some implications for us when we start to look at more specific types of energy. So, for example, looking at internal energy. Again, internal energy being the sum of all the different forms of energy in a system. We can calculate the change in energy, in internal energy, by looking at the final internal energy and comparing it to the initial internal energy. And the difference between those two would be the change in energy. in the context of that first law of thermodynamics, we know that if we experience a change in internal energy from our system, energy can't be created or destroyed. It has to come from somewhere. So what we introduce is this idea of the energy of the universe. And the change in the energy of the universe has to always equal zero. That's the first law of thermodynamics. Well, if we break the universe down into system and surroundings, that basically means that the system and the surroundings are going to be equal and opposite to each other at all times. If the energy of the system increases, it must have come from the surroundings. So the surroundings had to have decreased. If the energy in the system drops, that energy had to go somewhere. It must have gone to the surroundings, and the surroundings is higher. The two forms of energy are always going to be in this balance. Because in the end, their sum has to be zero. Otherwise, we violate the first law of thermodynamics. And so that's where our definitions start to become really important. What qualifies as a system versus its surroundings? Because if I recognize, oh, the temperature of my water went up. How did that happen? Well, I need to recognize, okay, if water is my system, the room is the surroundings. Is there a temperature difference between the room and the water? If there is, I can explain how the water got warmer or how the water got colder. It's a matter of energy transfer. And so one of the important things that we're going to run into in all of thermodynamics is the idea of something called a sign convention. Sign conventions basically tell us kind of implied meaning from whether a value is positive or negative. If energy values are positive, that means that energy is coming into the system. And if it's coming into the system, it must have come from the surroundings. And if our energy values are negative, that means that the system had to have given that energy away in some kind of way. And so if the system gives energy away, that means that the surroundings took it. So positive means that we're going into the system from the surroundings. And negative means that we are going out of the system. And into the surroundings. All right, let's take a pause here. And when we come back, we'll start to look at changes in internal energy from the standpoints of heat and work. And we'll get into applying some of those sign conventions and some other kinds of things as well.